Hi, my name is Eric Vallis, and I'll be doing an analysis of the paper Searching for Planet 9 with Co-added WISE and NeoWISE Reactivation Images by Meisner et al. 2016. In this search for Planet 9, we first need to ask ourselves, why Planet 9? Starting with the discovery of Sedna, scientists have found TNOs, or trans-Newtonian objects, that are orbiting the Sun with perihelia outside that of Neptune. The strange thing about these objects is that they seem to cluster in one direction. This leads scientists to believe that there must be a large mass on the opposite end kicking them into this orbit. This gives us evidence for Planet 9. Next, we need to take a look at the Nice model. The Nice model is currently our most widely accepted form of planetary formation for our solar system. In the Nice model, the outer planets, or the gas giants, start in much closer than their current orbits sit now. Uranus and Saturn actually have orbits that are switched. These outer two planets are also surrounded by a giant cloud of planetesimals. Gravitational interactions between these planetesimals and Saturn and Uranus cause them to get sent in towards the Sun or kicked out, which then interact with Jupiter and Saturn inside the solar system. These interactions, as Jupiter kicks these planetesimals back out of the solar system, cause Jupiter to slowly migrate inwards. Eventually, this causes a resonance with Saturn, which is unstable for the solar system to sustain. As we see in the video, this causes a scattering of the outer cloud as well as extension of the orbital reaches of the other planets. Although the sednoids can arise in this Nice model, it's actually strengthened with the addition of a Planet 9. Given the mass of the outer sednoids as well as their orbits, we can get a general idea of where the planet should be and what mass it should be at. The estimate given in the paper is between 5 and 20 Earth masses, as well as between 380 and 980 AU. Accounting for all of this, we would expect to find a detection of Planet 9 through visible means. However, some predictions seem to believe that it's going to be able to be visible at longer wavelengths, even down to the millimeter scale. Depending on which atmospheric composition model you use, it could even be detectable at 3 to 5 micrometers. This is important for how the team went about detecting Planet 9. Next, we're going to talk about WISE, NeoWISE, and NeoWISER. WISE, or the Wide Field Infrared Survey Explorer, is a telescope that operates in 4 different wavelengths. During WISE's original mission, it operated in 3.4 micrometers, 4.6 micrometers, 12 micrometers, and 22 micrometers. This WISE phase of the mission operated from January 7, 2010 to August 6, 2010. In early August of 2010, WISE began to run out of cryogenic hydrogen, which allowed W4 and W3 to operate at the 22 and 12 micrometers. It was in early August that W4 became inoperable, and then in early September when W3 became inoperable. After both of these two wavelengths were ruled out, the mission was called NeoWISE. That lasted from August 2010 until February 2011. In February, WISE went into hibernation until October 2016 in what was called NeoWISE Reactivation, or NeoWISER. The NeoWISER mission is operating at W2 and W1 at the wavelengths of 4.6 micrometers and 3.4 micrometers. Since Planet 9 is expected to be detectable between 3 and 5 micrometers, this team takes a look at the data from the W1 phase of the WISE mission. Since they're using this W1 data, they're able to use WISE, NeoWISE, and NeoWISER. WISE's orbit around the Earth is pole to pole and always at 90 degrees elongation to the Sun. This is important because it not only allows the solar panels to get constant sunlight, but it also allows the telescope constant observation time. The background image is a map of the entire night sky surveyed in infrared via WISE. It is important that WISE takes many observations over this time period and maps the entire sky for many reasons. Even though Planet 9 is thought to be detectable between 3 and 5 micrometers, it's probably going to be too faint for the WISE mission. This paper takes a look at adding multiple exposures together in order to increase the intensity of the brightness of the source. Since WISE is undergoing constant observation, it can take measurements from both sides of the Sun and use this parallax to help rule out some inconsistencies. Fortunately, this also gives us a threshold for where Planet 9 would be detectable. The animation on the left shows the WISE coverage on the entire orbit around the Sun. As each square gets lighter, that shows that it's increasing in exposure number. The higher inclination, the more exposures you get. Unfortunately, this is not where most of our current understandings of where Planet 9 would be are. These higher inclinations at closer orbital distance are also going to increase the parallax significantly. This also changes our threshold for detection. The image on the right shows our threshold for detection. As you increase in orbital distance, you can also increase in inclination. Above 800 AU, models are likely to be too faint unless far above the luminosity of the most optimistic models. Lastly, we're going to take a look at the methodology. The team utilized coaddition epochs, difference images, and Keplerian orbit fitting in order to see if they could detect Planet 9. As seen in the top right image, as well as the animation on the last slide, WISE's scan will overlap multiple times. The team took advantage of this by combining exposures in order to have brighter images, therefore increasing the likeliness of a detection. After looking at all the data, the team decided to bin all of these overlapping exposures into one-day intervals in which they called epochs. The image on the bottom left shows the number of exposures as a function of declination as well as right ascension per search area. The team then performed a series of filtering tests. The first of these tests utilized the parallactic smearing. We know that since Planet 9 would have to be at a certain orbital distance, anything moving too fast across the sky was automatically ruled out. They also performed outlier rejection tests, ruling out anything that was not consistent across exposures. Next is the difference images. Here, the team used reference scans such as 2MASS, as well as different softwares, HotPants and SCAMP, to extract difference images. Through this, the team was able to rule out any 2MASS sources, W1 sources, remnant artifacts, anything in the reference image that was too bright, negative fluxes, and ultrabright stars, which could produce glints. They also use this to get rid of latents, which are brightness holdovers between exposures. The image on the bottom right shows the number of transient sources per search area. The red dots represent the ones linked by Keplerian orbit fitting. The idea behind Keplerian orbit fitting is that Planet 9 would have to orbit at a certain rate. This forces our parallax and movement across the sky as a function of distance to match what our models would predict. In order to determine completeness, the team inserted thousands of transient sources in order to see what would get detected. These sources not only varied in brightness, but also in region density. The team found that in order to hit their 90% completeness quota, WISE would have to be around 16.6 magnitudes or brighter to be detected. In other words, this basically rules out Planet 9 as a candidate that can be seen brighter than 16.6 magnitudes at a wavelength of 3.6 micrometers to a 90% certainty. In these pictures, the top row is the Coadd epoch, the middle row is its subsequent reference image, and the bottom row is after the hot pants subtraction. Here we can see some of the many problems that the team ran into as a visualization error. On the far left, we have a glint. In the middle left, we see variable static sources that were not able to be extracted or filtered. In the middle right, we see a diffraction spike that was not filtered out correctly. And finally, on the far right, we see where a bright source was not fully masked. The team would like to do away with the visualization aspect and have it be purely software-based. However, this is not the case currently. Although there were over 400 detections, all can be either ruled out by Keplerian orbit fitting or by these mistakes through visualization mentioned. In closing, the team's main goal was achieved. They sought out to set a completeness threshold for which to check various regions of wavelength and search space. Although they did not find anything, they were thorough in their methods and their math seemed sound. It should be interesting to see what people can do with this methodology and to see where this methodology itself ends up.
Alright, how's it going, guys? So the team didn't find anything, and I think, maybe they just weren't trying very hard, so I figured I'd give it my best shot. So we know that the Planet 9 candidate is going to have a apparent brightness of somewhere between 20 to 25 mags in the visible spectrum. My telescope has a limiting brightness of around 13, somewhere around there. So odds are not good. I don't know if you can tell, but it's also quite cloudy. The modified Julian date is 52274. Time is 23:30 Central Standard Time. And we'll see what we got. Alright, so somehow the selfie camera does better in the dark. So we're going to go ahead and use that. We're going to look in the south-southeast direction. So the constellation Cetus is approximately where we are going to find it according to Brown and Bodigan. And it's going to be setting around this time. Let's see if I can get the pointer pointed at it. Alright, there we go. Right in that area. So that's where we're going to be looking. We'll see if we find anything. Here we go.